In this video, I'm going to prove every commonly used trigonometric identity in a way that you can just work it out on your own. No need to remember. After this video, I assure you that your knowledge about this matter will be both firm and secure, just like our border. So be sure to stick around until the end or you might miss something. I'll go through this as fast as possible, knowing that your attention span is identical to a 5-year-old.
Damn!
Let's begin. Taking a look at the Pythagoras theorem and a normal right triangle, we can say the following. Then we'll divide both sides by the hypotenuse squared. Notice something. That's right. We can equate the following expression that we obtained into the most commonly known trigonometric identity. Sine squared plus cosine squared is equal to 1. Also, you may notice that I put the power in between the function and theta. Don't worry, this is just a convention for labeling a trig function with a numerical exponent. I know there are many identities to take in right now, and there will be many more to come. But as I said in the title, we don't need to remember them. Just know where to come from. Also, if we consider dividing the expression with the adjacent squared or the opposite squared, two more or less commonly known expressions from the same family will be obtained. Notice how when I have the reciprocal of the trig function, I wrote down a different name for it. This is also another convention you should be mindful of. 1 over sine is cosecant. 1 over cosine is secant. 1 over tan is cotangent. Now we're going to prove more identities using inspection. I highly recommend you check out my second lesson of trigonometry first, because we're going to talk about trig graphs. It should be vital you have a good understanding of it first. As you can see, I have roughly sketched out the trig graphs. By looking at it, we can see that the cosine graph is symmetrical about the y-axis. From this, then, we can deduce the following. This is because for any negative value theta input, the output will also correspond to its positive counterpart. Similarly, looking at sine, we can see that the value minus theta will correspond with the negative of the output of the sine function. We can then say that sine negative theta is equal to negative sine theta. Such properties of sine and cosine make us classify them as odd and even functions. Sine is an example of an odd function and cosine for even. For the next one, we're going to have to go back to our right-angled triangle. Notice that I've worked out the other angle by using the fact that the total angle within a triangle is always 180 degrees. If we look respective to theta, we can see that the opposite side is the adjacent side for the red angle. This is the same for when we look at the adjacent side respective to theta. This means that the trig function value must be a bit different for the red angle. Let's look at the sine of the red angle. Sine of 90 minus theta is equal to side B over side C, but we also know that cosine theta is equal to the same thing. So we can say that these two are equal. Same thing can be done for cosine. We get cosine of 90 minus theta is equal to sine. Then dividing sine and cosine together, we get an expression for tan. Tan of 90 minus theta is equal to 1 over tan theta. Then we can also work out the identity for its reciprocal by simply dividing 1 to all of the identities we obtained. Again, no need to remember. Just remember the steps that were taken to get here. Replay the explanation again if you must. Memorizing too much will make you end up senile like Sleepy Joe.
Damn!
For the last sets of identities, we're going to look at a unit circle, as you can see from the illustrations. When we have an angle of theta in red and an angle of 360 plus theta in blue, it essentially represents the same point on the unit circle. Note that an angle of 360 plus theta is achieved by rotating counterclockwise to form a complete circle, then rotating once furthermore for angle of theta degrees. Therefore, sine and cosine of theta is equal to the sine and cosine of theta plus a multiple of 360. This is because the multiple of 360 represents the amount of times we rotated a full circle, and could also be either positive or negative, where a negative n may represent a clockwise rotation which forms a full circle. Since this doesn't cover every trig identity just yet, I'll return with part 2 later. Comment what you want for the next topic, like the video if you learned something, and see you lovely folks next class.